Hey everyone, so we just left off talking about speed and velocity. Now there was one last thing that I want to add to that, and it's this idea of relative velocity. So first I want to ask the question, just a thought question of how exactly do we find the velocity of an object? Now I'm not talking about the equation or anything. I'm talking about like how are we actually finding the velocity of an object? What does it mean when we say that something's got a certain velocity or certain speed? Another way of thinking about this, another question you could think of is, if you run on a treadmill, are you moving? And if so, how fast are you going? Are you sure? An idea of this relative velocity. Now, going back to what I said before about what is the actual speed, well, right now you're thinking of yourself as finding the speed relative to the Earth. Okay, that makes sense. But let's say we change where we're taking this perspective. Let's say we jump out of the Earth and now we're looking down from the moon. And we see now, even if you're, regardless of how you're moving, whether you're standing still or walking around, you are also moving with the rotating Earth. So the Earth is rotating at some speed from the surface of the Earth, of the moon. If we try to measure how fast you're going, it would turn out to be 465 meters per second, or a little bit over 900 miles an hour. Is that it? No, because if we step even further back and maybe we hop out of the solar system, we can see that that planet is actually orbiting, the Earth is orbiting around the sun at an even faster rate of 30,000 meters per second, or again, about 60,000 miles an hour. Um, Take a step back, the galaxy, the solar system is moving around the galaxy at some rate of 220,000 meters per second. And if we want to go along with the expansion of the entire universe, then the speed could go all the way up to 650,000 meters per second. So our speed is dependent on what our reference frame is. Where are we looking from, and what are the positions that we're comparing it to? Um, Now, let's consider a more down to earth type case. Let's say we're driving down a highway at 35 meters per second. This is about 65, 70 miles an hour. Maybe actually probably a little bit higher, closer to 75, 80 miles an hour. Now, you're driving down, all of a sudden, someone decides to bypass me. Could I figure out how fast he's going? The answer is yes. If I know how long it takes for his car to pass by my window, I can then figure out, if it takes a certain amount, like a 1 second to pass by, I could figure out what his speed based off of the average size of a car, and then compare that to my own speed. If he's going 5 miles per hour faster than me based off of how fast it takes for him to pass by my window, then I can tell that his speed is going to be, if I said 5 miles per hour, 5 meters per second, then I know that his speed is actually 40 meters per second. So we can actually figure out based off of this. And that's kind of related to this relative velocity. Now, I have a few videos here. I'm not going to show them all, mainly because they're a little too long and you can watch them yourself. But there are a few ones that I want to point out. So this is one that has really good visuals of what's going on. So in it, there's two cars, a Prius and a minivan. The Prius is 13 miles per hour. The minivan is 24. So first, the drone's taking a shot of both cars relative to the Earth. So we can see that the minivan bypasses the Prius by the time it reaches the end, and the because the drone is just hovering there, the Earth's not moving. Now the drone's actually moving along with the Prius. And now what we see is that the speed of the minivan is going a lot slower than it was before. And in fact, if we did the math, it would turn out that the minivan looks like it's actually going 11 miles per hour, while in the first case, the top case, it was going 24 miles per hour relative to the ground. So this is the type of scenario that we end up having. And then this is just, the clip from the perspective of the Prius. So I just want to show that. There's a few other ones that are really good. Like I said, they do coming from different perspectives and how the relative speed changes. I really recommend watching this. This is the link to the visual only clip that what I'm showing here. But you can actually find the full video called "Flipping the Classroom," Flipping Physics. Really interesting. There's a MythBusters one. I'm not going to play it right now. This one I also want to play really quickly, just for the visuals. So here we have a case of a car driving along a stationary surface. So this is the second type of relative velocity. If instead, oh, so if instead we have a scenario where the surface actually does move along with it, what we can do is we could figure out what the ultimate resultant is, what the ultimate velocity is based off of a vector diagram. So what we can do is we can draw the vector of the boat, relative to the water. So if it's going straight, that we draw that arrow straight. Then we include the velocity vector of the water relative to the Earth. And then the resultant of those two vectors, this diagonal here, will be how someone from the surface of the Earth will perceive the motion of that boat as it passes through this moving water. What I like about this is when he shows the example of on a treadmill. So again, originally it was going straight to that X. Now when he releases it, the treadmill is going to start pulling it downwards or to the right as the car tries to move along it, resulting in this diagonal path. So as we could see here, instead of going straight forward, it starts going on this diagonal path because of the motion of the surface. So these are the two different types of relative speed, relative velocity type questions. One where you're comparing two moving objects, and one where you're comparing oh, an object moving along moving along a moving surface. So just to clarify with this, I want to go quickly of how you'd figure this stuff out. When you're dealing with two moving objects, my main recommendation is you're either going to be adding or subtracting the two velocities of the objects, depending on orientation. Now, it can be a little tricky to figure out when to do it. When are we adding? When are we subtracting? One way you could figure it out is by drawing a quick little diagram. Essentially, you can kind of do something where if you have a car and another car, one's going 25, the other one's going 35. What you can think about is how far these two cars travel after 1 second. So this car moves forward 35 meters. This car only moves forward 25 meters. So in total, this car is going closer to the other car at a rate of 10 meters every second. So we can get the relative speed, and we can see that we are going to subtract them because as this one moves forward, this one also moves forward. So we take the difference of that motion, uh, as opposed to a scenario like this, where we have the 35 going forward and a 25 going forward, and now they're moving towards each other uh, at a rate of 60 meters every second. Besides drawing it out, you could also use subscripts. So, for example, a common way of writing the speed of A relative to B is writing it like AB. So, just like you would say this phrasing, that's where the order is. The velocity of A relative to B. And then to figure out what that is, you would do the velocity of A minus the velocity of B in the order of the subscripts. If I decide to flip this and I want to know about the velocity of B relative to A, then it would be velocity B minus velocity A. Note that these are velocities, not necessarily speeds. Even though I've just said speed before, these are technically velocity, which means direction matters. I actually had this little simulator to kind of show some of this relative speed. And it really kind of points like what's going on. So here I have two objects. I have a mass 1, mass 2. Doesn't matter what their weights are. What matters is that mass 1 is traveling to the right at 1 meters per second. Mass 2 is moving at 0.5 meters per second. If I play this and I wait until right before they're about to collide, we can see that the collision is going to occur at about 2.65 seconds. So 2.65 seconds. And that's for 1 meters per second and zero point 0.5. Now I'm going to readjust this and I'm going to do the relative velocity of 1 relative to 2. So because 1 was initially at 1 meters per second and 2 was at 0.5, that means that object 1 has a relative speed of 0.5 meters per second. Again, doing the same typical math we did before. The velocity of 1 relative to 2 was 1 minus 0.5 is 0.5. If we do the same thing, now this object's moving slower, it still has to cover the same initial separation, and it turns out that the time it takes for it to collide is 2.65 seconds, exactly as we saw before. So this is the nice thing about relative velocity, is that if you have a scenario where you have two moving cars, you can just treat it as if one of the cars is stationary and it's the other car that's moving towards it. And it simplifies the problem tremendously. Now, I already showed an example of the second one. This was the boat. Again, it really comes down to drawing the vector diagrams. You just want to make sure that you note which one's the actual resultant and make sure that you're drawing your vectors properly. So we'll do a few practice problems in a second. This little animation kind of shows the three examples for, I guess, plane rides, if you will. So in all three cases, the plane is traveling at the same speed. However, you'll notice that they have different motions. One's moving forward, the other one well, they're all moving forward, but one's moving really fast, one's a little bit slower, one's going on an angle. What's going on is that each one is being exposed to a different amount of air uh, wind speed. So the one on the left is actually getting wind coming towards it from the back, propelling it forward a little bit faster. So if its original speed was 100, the wind adds on an additional 20 miles an hour, let's say, to make it go faster. Here, the middle case where it's traveling slower, it's got what's called a headwind. So this is actually subtracting that speed, giving us a net speed of 80, fairly small. In this scenario, we end up getting that vector setup where now it's going off on an angle, and we see it here. So this is pretty much the idea about the relative velocity when you're on a moving surface. That surface is going to either speed you up, slow you down, or kind of change your direction according to the orientation. So we'll do a few practice questions. Pause video, work itself. We'll go over in a second. All right. So in the first question, they want the velocity of one relative to one. So that's just zero. If we did the math, v1 1 is v1 minus v1, so it's zero. For number two, so the velocity of car one relative to car two, we're going to do it the order 50 meters per second is the speed of car one, minus 65 meters per second for car two, and they're going west initially. So we get a relative speed of negative 15, which means that relative to car 2, car 1 is moving at a speed of 15 meters per second east. Now this makes sense because car 2 is moving faster than car 1, meaning it's pulling away. So from the perspective of car 2, if you looked out the window and you were staring at car 1, you would see car 1 slowly moving further and further away from you. And it would look as if it's moving 15 meters per second in the opposite direction, east. That's what we're getting in this setup. This is what this relative velocity is telling us. Here's the next question. Pause the video, work on yourself, and we'll go over in a second. All right, so in this case, now it's slightly different. Now we have two cars heading towards each other. And again, you have to remember that these are velocities. So when we're doing car 1 relative to car 2, this time we're going to add it. And that's because of the fact that technically what we have is this scenario, 50 minus, and then because the 65 is going east in the opposite direction of the initial case, I now have to make this as a negative 65 to note that this velocity is in the opposite direction of that 50. So negative minus a negative gets me a plus. So that's why it's now being added when they're moving together. And we get 115 meters per second west. Because of the fact that the 50 is my positive number, and that was going west, and the number I'm getting here is once again positive, then my final answer is going to be positive. Again, easy enough. Car 2, do the same thing. This time switch it. It becomes 65 plus 50. So now we get 115 meters per second east. Again, the 65 is going east. That's the one that we're denoting as positive. Yada, yada, yada. All right. So this is kind of like how it can really help you dealing with the different types of relative speeds, whether it's coming towards or in the same direction, when to know when to add, when to subtract, all that good stuff. All right, here's the next question. Pause the video, work itself. I'm going to go over in a second. All right, so for this one, this is that second scenario where we have an object moving with the like a moving substance, moving surface. Here, that surface is the air, the wind. There are a few things that we have to be careful of. For example, it says that the wind is coming from the west. That means that this is pointed eastward. Um, Now, in order for the plane to point directly north, it turns out that we want the plane to actually be pointed northwest. Um, we'll see why when I draw out the diagram, but one way to think about it is that this wind, if the plane continues moving forward at its initial speed going directly north, when this eastward wind comes towards it, it's going to start pushing it east. If we want to maintain that north direction, we need to find a balance and try to counteract that eastward wind. So by pointing the plane towards the wind, we can kind of cancel out the effect the wind has on the motion, on the path of the plane. So that's why we kind of want to point it northwest to kind of get the east canceling out the west. Now, if I drew out what I was going to do, again, I want the 100 kilometers per hour to be my resultant. So that one's going directly north. Now, because this is my resultant, that means all my arrows have to start here, or the path that I create with my arrows is going to have to start here, and it's going to ultimately have to end here. So what I'm going to do is at the bottom, I'm going to draw the wind vector, 25 kilometers per hour east. And then because I have to bring this, the arrow to the finish line, like I started here, I went this way, I had to get back to this finish line that is pointed out by the resultant. This ends up being the path that the plane actually has to take. So how do we figure this out? Well, I just created a right triangle. This is the hypotenuse, so I could do Pythagorean theorem. I'm not going to show the work for this only because I don't have the room for it. But if you do Pythagorean theorem with these numbers, you should get about 103 kilometers per hour. So the plane will end up going a little bit faster because of this added wind. Or it would have to go a little bit faster to counterbalance the added wind to it. To find the direction. Now, I should have been a little bit clear about the direction because I need to tell you relative to what specific point. This is the direction that we're actually referring to. Typically, whenever they want an angle direction, you want to try and give it with respect to the x-axis. So here I'm trying to find this angle because this is my x-axis. From here you could do SOHCAHTOA, so either sine, cosine, or tangent. I'm going to do tangent. The way it would be set up as tan theta equals opposite over adjacent. So we have tan theta equals 4, inverse tan of both sides, and we get that the angle is 76 degrees northwest. So this is what you would do to get a more accurate direction. All right, and that's pretty much it for relative velocity. The next thing that we're going to talk about is acceleration, and it's a pretty straightforward. It's actually where the questions will start to get a little bit more interesting. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.